Okay, today we're going to be talking about the Pythagorean Theorem. Now, the Pythagorean Theorem is a property that applies to right triangles. Now, a right triangle is a triangle that has one right angle or 90-degree angle, like this one right here. Now, this is a right angle right here, and the reason why is because it's like, okay, you're going down and then immediately, all of a sudden, you're going left. So this would be a right triangle. Now, A, B, and C are the sides, and of course each individual side has their own length, and the Pythagorean theorem has to do with side lengths. It has to do with how long each side is. So, let's go ahead and go into the Pythagorean theorem. No, okay, before I actually do that, I should say A and B are called legs of the right triangle, and C is called the hypotenuse of the right triangle. So the hypotenuse is always going to be opposite of the right angle. A and B will touch the right angle, but C will not. Okay, so let's go ahead and go into a statement of the Pythagorean theorem. If A and B are the sides, the lengths of the sides, lengths of the legs of a right triangle, and C is, okay, something strange going on. Okay, I guess it's okay. C is the length of the, okay, I'm going to need to get some line breaks in there, obviously. C is the length of the hypotenuse. Then, okay, so I'm going to go ahead and put some line breaks in there so you can see it. Okay, there's only one h in length. Then, and notice that I'm going to put a little extra space here. Okay, notice that this, if A and B, blah, 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 all this is doing is describing this right here. You have a triangle of length A and B for legs, and length C for the hypotenuse. Then, and this next line is the important part, the length of A squared plus the length of B squared is equal to the length of C squared. So think about what that means for a minute. That means that, and this is only for right triangles, that if you square the length of this side plus the square of the length of this side, take the square root of that, you'll get C squared. You will get the length of that. So that's kind of an interesting concept, and I'm sure you've seen this is a very big geometry problem. It's very common. And I'm sure you've probably seen this internet joke, find x. Well, here it is. You know, someone just said, circle x, and said, there it is. Well, this is actually a very common, a very classic Pythagorean theorem problem. So let's go ahead and work with that for a minute and see if, so we have, so for example, find x. And we're going to be doing the same find x that they're doing here. So that means we're going to have, and I'm going to see if I can get, okay, so we're going to have them both on screen at the same time. Well, don't want it to take up too much room. Okay, so let's see how this corresponds to this. Now let's also notice that we're talking about a squared plus b squared equals c squared. I want to keep all this on here at the same time. Hopefully that won't get overwhelming. So notice that 4 is a, 3 is b, and x is c. So we have that a squared, which is 4 squared, plus 3 squared, which is b squared, which is 3 squared, equals x squared. X is our unknown. X is what we're trying to find. So 4 squared is going to be 16. So we have 16 plus 9, because 3 squared is 9, equals x squared. X is still unknown. So that means we go ahead and add these two, and we will get 25 equals x squared. And x square root of 25 is equal to 5. So x equals 5. Now, you may be thinking, why is it that you don't put plus or minus 5? Whenever we take the square root of both sides of an equation, we always put a plus or minus here. Well, the reason why we don't in this case is because this is a length. You can't have a negative length. If we were to say that this was of length -5, you would probably need to be committed, because that doesn't make any sense. There's no such thing as a length of -5. So whenever we're dealing with the Pythagorean theorem, our answer is going to involve positive numbers strictly. Okay, so now let's deal with a variation of the classic problem. Okay, so let's go ahead and we're done with that. So let's deal with the variation of the classic problem. Example, variation of the classic problem. So let's say we know that C equals 5 and 3 equals, and B equals 3. Okay, so C equals 5, so this is 5, and B, let's move this a little bit, so we have C is equal to 5, and C is equal to 3, C is equal to 5, B is equal to 3, and now A is our unknown. This is very similar to the problem we had before. Actually, it's pretty much the same, except that instead of finding C, we're finding A. So, okay, so what we have here is, we don't know what A is, so we have A squared plus B squared, which is 3 squared, equals C squared, which is, this was going to be 5 squared. Okay, so now let's go ahead and clean this up a little bit here. So we have A squared, still A squared, we can't do much with that yet, plus 9 equals 25. So then that will mean that A squared equals 16. I just subtracted 9 from both sides. 25 minus 9 is 16. And so that A equals 4. Because, of course, you take the positive square root. So that means we know now that A is equal to 4. Okay, so that is the variation of the classic problem. Now, let's go on to a different one. This is the scandalous problem. And I'll get into why it's called the scandalous problem in a little bit. It's kind of an interesting story about the history of math. I think it's interesting. It is interesting. It's a good story. So, now our problem is that A is equal to 1, and B is equal to 1. So, that means we have A squared plus B squared, which is 1 squared plus 1 squared, equals C squared. Oops, C squared. So, also think of it this way. What this means is we're finding the length of the diagonal of this square. So, this is a square of length, side length A. In this case, A equals B. Now it doesn't look exactly like that here because I didn't draw this like a perfect square, but let's pretend that it is. So A equals B, so that means we have 1 squared plus 1 squared equals C squared. So we're finding the length of the diagonal of this square. So that means we have 1 squared is 1, so 1 plus 1 equals 2, so 1 equals c squared. I'm sorry, 2 equals c squared. So that means that c equals the square root of 2. And this square root of 2, this is why it's called this is why I call it, I should say, a scandalous problem. This actually goes back to the history of the Pythagoreans. This is called the Pythagorean identity. Not the Pythagorean identity. The Pythagorean identity is something from trigonometry. The Pythagorean Theorem. The Pythagorean Theorem was discovered by a group of people called the Pythagoreans, of course, and they were called that because they had a single leader who was named Pythagoras. And Pythagoras started this group, and it's basically a math cult. I know that sounds strange, but they had very strong religious beliefs based on math. So Pythagoras was just almost the Jim Jones of his time. This was a very eccentric cult. And obviously you're not going to be tested on this, but it's a funny story, so I thought I'd say it. And one of the basic beliefs of the Pythagoreans was that any number can be expressed as a ratio of two whole numbers. So that means that you can express any number as a fraction. But they discovered this theorem, that the Pythagorean theorem, and they used it to find the length of the length of the diagonal of a square with side length 1. And they found that it's equal to the square root of 2. But you can't express the square root of 2 as a ratio of two whole numbers. So that was kind of a threat to their faith. It was a scandalous thing to think that the square root of 2 can't be expressed as a ratio of two whole numbers. So they hid this. This was like a conspiracy theory of their time. It was very strange, but of course, eventually it did get out, because something like that couldn't be hidden very easily. And actually Plato talked about it a little bit. I'm not sure where Plato talked about it. He wrote a lot of different stuff, but Plato once said, and I hope I get this right, he is not worthy of the name of man who does not know that the diagonal of a square is incommensurable with its side. Now, if we take that to be literally, that would mean that none of us is worthy of the name of man, because none of us really know what he meant when he said that, because nobody knows what incommensurable means. Now, what he means is that if you have a perfect square, let's see if I can draw it. Not quite. Well, that's kind of a weird hyperbolic square, maybe. I'm more impressed with myself than I thought I would be. That's kind of close to a square. So that means that if you have a perfect square and the side length, you have a side length that is a whole number, then the diagonal is going to be an irrational number. And if the diagonal is a whole number, then the side length will be an irrational number. That's what Plato meant when he said that the diagonal of a square is incommensurable with its side. Now, don't take that personally, because Plato had very high standards, of course. I didn't know that until, pretty recently, I guess. So, anyway, Plato was really big on math. It was kind of one of the things that makes him more interesting. So that completes the scandalous problem. Let's get rid of everything that I just drew in. So let's go to one more example, a less than classic example. So let b equals 5 and c equals 10. Oops. b equals 5 and c equals 10. Okay, so now we want to find a. Okay, and of course we can't just go circle this and say, here it is. We can, but we won't get any points for that. okay, let's go straight into it. So a squared is unknown. So we say a squared plus b squared is 5 squared, equals c squared, which is 10 squared. Okay, a squared is still unknown, plus 25 equals 100. So let's subtract 25 from both sides. We'll get that a squared equals 75, or that a equals square root of 75. Now let's go ahead and find out what the square root of 75 simplifies to. So 75, we can take 3 out of 75, and we'll get 25. And 25 is 5 squared. So you have one pair of 5s you can pull out front. So that means that a equals 5 square root of 3. So that means this is our answer. This is what a is equal to. Okay, now I want to do one more example, and after this example I want to say something that's I think is kind of interesting, but after this example is the end of testable material. And let me go back to this one time. This is the kind of thing that you'll probably see more often in like tests, and not tests, in homework, because you have 75 squared. Sorry, not squared. Square root of 75. Instead of getting a nice clean answer like square root of 2 or 4 or 5, you get a equals 5 root 3. More often than not, this is the type of answer you'll get. Okay, so now for one more example. This is one that I don't want to finish, but it's still one that, and the reason why I don't want to finish it is because I want you to try to finish it, but I want to get you started on it because it's a very unusual type of problem. Let's say c equals 15. Okay, so far so good. But a equals 2 times b. So that means that we don't know what a is. We only know that it's twice the length of b. So instead of writing this as I'll just do it. So we have a squared. So a squared is 2 times b. So we have a squared is 2b squared. Then b squared equals c squared. Oh, and c is 15 squared. Okay, so now we have a single fairly simple equation involving one unknown, and we can solve this using the methods that we were using before. In particular, we would probably use the square root property that we talked about. I think that was 9.1. Yeah, it had to be 9.1 because 9.2 was quadratic. So this we could solve using the square root property, and then once you find out what b is, you can find out what a is. Now I don't want to finish that up for you because I want you to go ahead and be able to do it on your own. But now I want to go ahead and go into one other thing. Now, I'm not going to be talking about this next part in class. It's kind of a YouTube exclusive. But also, this is what I'm about to talk about is not testable material. So, if your brain is full, I understand, and you don't need to worry about taking notes on this next part. I just think it's kind of interesting. Now, the reason, whenever we take, we call this, we say, let's not do 3, let's not do 2, let's do 3. So we say that this is 3 squared. We say to the power of 2 is squared. Well, why is that? Well, let me draw a box. Okay, now this box has side length 3. So it means I can separate it into 3 units. 1, 2, 3. Okay, so I'm going to go ahead and draw all the individual boxes that make this up. See if... Okay, so each one of these individual boxes, I know I didn't draw it perfectly, but each one has side length 1. This, however, the box as a whole has side length 3. So that means you have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes total. So what that tells us is that 3 squared equals 9. And we have 9 boxes. So what I'm getting at is that 3 squared, we call this squared because this tells us the area of a square of side length 3. So I'm going to repeat that because that's pretty important. I mean, we're not going to be using it a whole lot in this class, but it's pretty important to geometry, it's important to trigonometry. So whenever we have a square of side length 3, we find the area of that square, or it doesn't necessarily have to be 3. Let's get rid of this 3. Let's just call it C. Of side length C. Okay, so that means all this stuff goes away. The area of that square is equal to C squared. So that means you could fit in C squared boxes of side length 1 in there. That's what that's telling you. Okay, so that means that the Pythagorean theorem, and I'm going to go ahead and erase this stuff. I'm going to clear off all that stuff. The Pythagorean theorem is, okay, let's see if I can do this on here. No, I'm going to do it separately. Keep this the way it is and try to recreate this. This is not going to be perfect. But the Pythagorean theorem is telling us, okay, let's make a box, let's make a square, a perfect square, a semi-perfect square, with this, with each individual side. Okay, so what the Pythagorean theorem is telling us is this is a squared, this is b squared, this is c squared. So the area of this box plus the area of this box equals the area of this box. And notice, of course, that each of these is a square. That means that each of these has the same side length as the side of the triangle that it's attached to. Okay, now I want to get into something of why the Pythagorean theorem works. Okay, so let's take a look at this right here. Oh, I'm going to clear that off. Okay, so this thing right here. So I think we can agree. Let's go ahead and say that this is side length. It has side length A. Let's say this is side length A, and this is side length B. Okay, now let's describe a few things. So, sorry, I'm gonna get rid of that. Okay, so if this is of length A, then this is of length A, and this is of length A. So this part right here is A squared. So let's see if I can type this in. A squared. Okay, it doesn't look quite right, but this caret symbol right here, that means A squared. That means this area is A squared. And this is also a box. So since this is of length, oh gosh, I better start this over because I'm starting to confuse myself. So this length is A, and all of these triangles are identical, I should say. All 4 of these are completely identical, so that means this is length A, this is length A, and since we're talking about right angles here, this is a box of area A squared, because this is A and this is A, so A squared. This is of length B, which means that this is length B, this is length B, this is length B, and this box here is B squared. Okay, so what we're saying here now is that I'm going to bring in another copy of this. Okay, and let's move that out of the way. This is set to always on top. Let's take that off. So, no matter how we move these triangles, like I can move them down here, I can rotate them. Oops. This program's kind of hard to use. I wonder if there's like a select tool. I don't even know if there is. I can rotate any individual triangle. Let's see if I can find out which triangle is which. No. No. Here we go. This is what I'm looking for. I can rotate any individual triangle. But the bottom line is, if I move them, if I rotate them, they always take up the same amount of space, just so long as they don't overlap. Which means that the total area of this box is going to be the white space plus the blue space. So let's see if I can get this down here, so I can type it up in a place where you can see it. Whoa, did not mean to do that. Oh well, let's put it at the bottom. We'll say total area of square is blue space plus white space. Okay, so now let's scroll up on that. Okay, so total area of the square is the blue space plus the white space. So no matter how we move these triangles around, they're always going to be they're always going to only take up the same amount of space. So that means that the total area of the white space, so let me put this in terms of an equation. So total area of square equals the blue space plus the white space. So that means that the total area, let's see if I could write this the way I'm trying to think of it. So that means that the white space is equal to the total area minus the blue space. Okay, so let's go back to these two, that's not the right one, these two images. So the total area of the square is the blue space plus the white space. Okay, we can see that over here. But that also means that the white space is equal to the total area of the square minus the blue space. And no matter how much we move this stuff around, the blue space is going to stay constant. So let's play around with these and see what happens. Let's take this and let's move it so we get it right here. Now I'm going to make these so that they don't overlap. Obviously, if you make them overlap, then these statements are not true. But that's going to not happen in the end. Okay, so we don't want to rotate that. We just want to move it over here. And let's take no, not that one. This one. Okay. So, notice something. These triangles haven't changed length at all. So, that means that this is still side length C. This is still side length A. And this is still side length B. And the white space hasn't changed. So, that means that this middle part here is C squared. So since the white space hasn't changed, the white space is the same amount, In both of these individual pieces, the white space is equal to the total area of the square minus the blue space. But the white space over here is c squared, and the white space over here is a squared plus b squared. So this is a visual proof of the Pythagorean theorem, and I always thought that was kind of an interesting way to view it. You may not agree, but at any rate, remember this is not something that you're going to be doing on a test, but it is something that's still kind of cool, so I thought I'd go ahead and share it. So that concludes this lecture. I'll see you in the next video.